Alright guys, let's continue with chapter 12. We were speaking in the last video about evaporation, condensation, freezing, melting, sublimation, and deposition. Today let's consider evaporation. There's a point at which, in a closed vessel, you'll reach dynamic equilibrium. So if we look at this Erlenmeyer flask, which is sealed, by the way, notice that it is stoppered. Evaporation will begin to occur when the molecules that are closest to the surface reach the energy level. They have enough kinetic energy to escape from the liquid phase into the gas phase. Because this is stoppered, they're going to get trapped inside this vessel. At some point, they will start to condense again and turn back into liquid. When the rate of change from liquid to gas is the same as the change from gas to liquid, we've reached dynamic equilibrium. Now this is important from the perspective of vapor pressure. So vapor pressure is defined as the partial pressure of the vapor, so the gas phase, that's in dynamic equilibrium with its liquid. This will increase, so you can have a higher vapor pressure when the temperature becomes higher, or if you decrease the strength of the intermolecular forces. It is independent of surface area, and this is because, you'll remember, let's go back to our little diagram. Dynamic equilibrium is when these two rates are equal. So when the change to a gas is the same as the change from a gas to a liquid. So if we increase the surface area, it won't matter. To be at equilibrium, it has to be the same rate of change. So the rate of change will be equal whether it's in a very small Erlenmeyer flask or a very large Erlenmeyer flask. Boiling is when you've managed to get enough thermal energy to cause the water molecules inside this liquid to change into a gas. And this is why when you have a pot of water on your stove, you're making some pasta, it starts to boil, you start to see those little bubbles coming up from the bottom. These are the water molecules that have actually attained enough energy to change into gas. Now, a heating curve demonstrates the change that a substance goes through in phases, as well as what's happening to the temperature and the energy levels. So if you look at this diagram, we start with a pure substance, and we're going to boil this substance. Notice that the substance keeps increasing in temperature until it actually reaches the boiling point. And you can see that it plateaus at this point, and then it starts to increase again. So at boiling point, you are absorbing energy so that these particles can break away from the liquid. So energy absorbing is happening here. I'll just put absorb energy. All right, and the same will happen at the freezing point or the melting point. We're going to see a plateau at those points as the bonds are broken and reformed. Heat of vaporization is also something that we need to consider, and we can actually do some calculations with this. So the definition is that it's the amount of heat required to vaporize, that means to change it from liquid to gas, of 1 mole of liquid at a certain temperature. So during evaporation, we're going to have a positive delta H vaporization, but when it's condensation, it's negative, because remember, those processes are endothermic and exothermic in that order. So evaporation is endothermic and condensation is exothermic. So here we have the heat of vaporization of water. You can see that when we change it from a liquid to a gas, we have the delta H as 40.7 kilojoules at 100 degrees Celsius. So this is kilojoules per mole. If you were given less than a mole, you would have to calculate how many moles you have. So for example, I could give you a mass and you would have to calculate the moles and then figure out how much energy was necessary. Now for the exothermic process of going from a gas to a liquid, condensation, you're going to have a negative delta H vaporization. And you can see in these charts that depending on the substance and its boiling point, you're going to have a different amount of heat necessary to change that 1 mole, either from liquid to gas or gas to liquid. So let's do a problem. We have a substance, we have water that is being vaporized at its boiling point, so that tells you 100 degrees Celsius, and we are given 155 kilojoules of heat. We want to find the number of grams. So let's start with what we are given. We have 155 kilojoules. Now from the previous information that we got, we know that it takes 40 kilojoules per mole of water, so let's put H2O here, to cause vaporization. And this would be a positive value because it is going from the liquid state to the gas state. And then we want to know how many grams it is, so you have to remember that there are 18.02 grams of water in 1 mole of water. Okay, so let's do the math. I've got my calculator here. 155 and so the answer that I came up with was 69.8275, and this would be grams of water, okay, because this cancels, this cancels. Now notice that we used the 40 kilojoules, the other, all of those are constants other than our given value, so let's go to 3 sig figs. We'll have 69.8 grams of water. Okay, I want you to try the Mastering Chemistry now. Good luck.